Hello, and thank you for watching. My name is Doug Lombardi, and I'm an associate professor in the Department of Human Development and Quantitative Methodology at the University of Maryland in College Park. I'd like to thank APA Division 15 for the 2019 Richard E. Snow Award, and I'd also like to thank the National Science Foundation for helping fund some of the research that I'm going to be talking about today. Additionally, there are many people to thank. There are over 50 people in this image who have collaborated with me over these almost 10 years of educational research. These include researchers and faculty, students, teachers in the classroom, and mentors. One of those mentors is Gail Sinatra, who has guided me since I started my research program at the University of Nevada in Las Vegas. She's been a great mentor, a great colleague, and a great friend. I'd also like to thank Dr. Janelle Bailey at Temple University, who is a research partner over these past 10 years, and has also been a life partner with me. I've had previous careers prior to becoming an educational researcher. In those years, I was an applied researcher at a major federal laboratory. I worked for a NASA mission, and I was a classroom science teacher. Those experiences have guided my research program. And they've guided the hope that my research can help inform, in some small way, instructional design by applying research theories and to help people become more scientifically literate and to equitably solve local, regional, and global problems. Even though my research is contextual in social scientific issues and also contextual in classroom context, it has a strong foundation in psychology and learning theory. Some of that learning theory has been frameworks that I've developed with my colleagues, Michael Nussbaum and Gail Sinatra. This social cognitive model is about epistemic judgments, and it's particularly about epistemic judgments on knowledge claims. We call that judgment, when it relates to science, the plausibility judgment. It's different than other epistemic judgments that may impact source. There's a wide literature and a wide research community that does sourcing work. What we do is a little bit different than the sourcing folks. At the heart of this model, this framework, is the notion that people's cognitive evaluations can influence their plausibility judgments about knowledge claims. Oftentimes, those judgments are made without little evaluation, and they can be an automatic process. But instruction or other modes to make that evaluation more explicit can help rethink and make a more reasoned plausibility judgment. So again, plausibility is just one type of epistemic judgment. Others that relate to source include credibility or reliability. Certainly they're related to plausibility, but they're fundamentally different. Some of my empirical research has shown this relation and shown these distinctions. Plausibility judgments emerge from these cognitive and social evaluations about knowledge claims. So what do I mean by a knowledge claim? Well, that can be an explanation from a scientist. It can be a theory. It can be a hypothesis. So, for example, these dogs from this Far Side cartoon are trying to explain how doorknobs work. The doorknob principle is a knowledge claim, a principle of how the doorknob works. They're collecting evidence. They're trying to do it reliably, and they're trying to be credible about it. That is more of a source or an evidence evaluation. Again, the plausibility of the doorknob principle is a knowledge claim. So what do we do in our classroom environments? Well, we use instructional scaffolds to help facilitate students' evaluations to be more explicit and more scientific. And we do this through the scaffold called the Model Evidence Link Diagram, or MEL for short. This MEL diagram is a pre-constructed diagram. We call it the PCMel. And the form and structure of the MEL diagram was developed by researchers at Rutgers, Clark Chin, Rick Duschel when he was there, Ravit Gul and Duncan and their colleagues. And the way that students evaluate is they evaluate the connections between lines of scientific evidence and two alternative models that explain a phenomenon. In this particular pre-constructed MEL diagram, they're looking at two different models about the utility of wetlands. Are they a nuisance or do they provide important ecosystem services? And students base it on four categories of evaluation between the evidence and the explanation. The evidence supports the model, strongly supports the model, contradicts the model, or has nothing to do with the model. And then we do this not only with water and water resources like wetlands, but we look at other phenomenon that related basically to environmental and earth science issues, such as climate change and extreme weather conditions, fracking connection and earthquakes, how fossil evidence can give us inferences about paleoclimates. And we also do it on other controversial issues, for example, the origins of the universe. Over these past years, we've involved teachers and secondary students, that's middle and high school students in the United States. Over 1,000 of these students have been involved in this design-based and quasi-experimental research. We've been in various classrooms in the Mid-Atlantic and Northeast United States, the Southern United States, and the Southwest United States. Those have included urban, suburban, and rural classrooms. Currently, we're developing a new form of the scaffold to increase students' agencies and hopefully increase the quality of their evaluations and their learning. These are called the BuildAMel Scaffold. And what students do is they construct their own MEL by selecting 4 lines of scientific evidence from a possible 8, and they select 2 models to explain a phenomenon out of a possible 3. One of those is a scientific model. What I'm going to show now is a video clip of students. These are 3 students, they're middle school students, that are working on the BuildAMel diagram around fossils and how that gives us inferences about paleoclimates or past climates. These 3 students, primarily the student that you'll see will be this student. He'll talk right at the beginning. You won't hear him extremely well. It's very difficult in classrooms to get really great audio recordings, and that's one of the challenges that we have in our research, is making really high quality transcriptions of what happens. This student will talk, and they'll talk about how they're interpreting the data, and the other students are going to kind of be participating. Normally they do this in a more collaborative mode, but what you'll hear predominantly is kind of the teacher's facilitation of this.
That it contradicts because it doesn't really say anything that doesn't support it. It just sort of doesn't say.
Right? It doesn't really give you it doesn't. There's really. It's hard to contradict it, but it's because it's not like a. It's not really telling. You don't really know for sure that you're right, so there's really no way to really 100% contradict. We can't like go back in time to check.
So what the students do is they work through these diagrams together, and they do a variety of activities, not just the MEL diagram, but prior to doing the MEL diagram, they do some tasks, and after it, they do some tasks. For most of these tasks, the measurement that we do in a research mode is kind of embedded within it. It's hidden to the students, it's hidden to the teachers. The exception to that is the knowledge pretest and the knowledge post-test, which is very similar to a test that they might take at kind of a quick pop quiz. Part of the task include the model plausibility ratings task, where the students are introduced to the models and they make initial plausibility ratings to all, if it's the BuildAMel, all 3 models, or if it's the pre-constructed MEL, just 2 models. Then they either complete the PCMel diagram, the pre-constructed MEL, by drawing the arrows, which is their evaluations of the connections between lines of evidence and the 2 alternative explanation, or they construct their MEL by considering all of the lines of evidence and all of the different model options that they have, and then they construct their own MEL and evaluate it. After they have constructed their MEL diagram, they re-rate the plausibility of the models, and they provide explanations about why they drew the arrows that they did. So from that we call that the explanation task, we get evaluation scores. Model plausibility ratings give us ideas about how the plausibility shifts. And of course, the knowledge scores give us an idea if their knowledge has changed over the course of the activity. In our first MEL project, 3 years of National Science Foundation funding, we conducted a quasi-experimental component in the last year. And the results revealed that the pre-constructed MEL in this case led to plausibility shifts and increased knowledge when compared to 2 other tasks. One of those tasks was the model evidence link table, which is basically the same format as the MEL diagram. It includes 4 lines of evidence and 2 alternative models, but it's in a tabular format where the students do not draw arrows, but they just indicate codes in a table. We also compared it to the monomel, which is a MEL diagram with just 1 explanation. 4 lines of evidence still, but 1 explanation, and that's the scientific explanation. We saw that the MEL resulted in nice plausibility shifts about a category. The MET did as well, the table format. The monomel, no plausibility shifts. Similarly, we saw gains in knowledge scores. The MEL and the MET were about the same. The MEL was slightly stronger in its effects. Currently, we're working on doing tests of the BuildAMel. We're in a pilot test phase. We're actually just completed year 3. So we've gathered data in years 2 and 3. And we're getting ready to do more testing in year 4 and year 5. In this, we show that we're seeing a slight advantage. Now what we're doing is we're comparing the BuildAMel to see if we're getting increased levels of evaluation over the pre-constructed MEL and increased shifts in plausibility and knowledge. So the BuildAMel does result in this, and we can see here now we're seeing distinctions between middle school and high school. We see the slightly lower levels with middle school, but we're seeing comparable shifts from pre to post. So we see some nice shifts here. This is not really a shift. This is the evaluation score, which we just measure in the context of the task. We're seeing enhanced evaluations from the BuildAMel. We're seeing strong plausibility shifts. Again, a higher comparison with the BuildAMel than the PCMel. And we're seeing nice knowledge shifts. One of the things even though they're nice shifts, they're not as strong as what we were seeing in the last experiment. So we're continuing to tinker in a design-based mode to make the activities really strong, not only just to make sure we're having them worded correctly and that they're structured correctly, but also to think about how they're part of the instructional format and how we train teachers. This is just another example to show you how the BuildAMel over here on the left is enhanced over the PCMel. These are complicated structure equation models. And really what I want to focus on is just this pathway versus this pathway. This really exemplifies the plausibility model, the theoretical model that I discussed earlier. And what we see in both of the models, the pre-constructed MEL or the BuildAMel, is that evaluations in and of themselves don't really relate to knowledge post-instruction. Really, it has to go through the pathway from evaluation to plausibility post and then to knowledge post. And what we're seeing again is that the BuildAMel is a little bit stronger. What's interesting here is that students aren't relying on their pre-plausibility judgments as much in the BuildAMel, and they're getting a stronger pathway between evaluation and knowledge post. You can see the comparison in these links here by effect size comparisons. Here we've got the freshwater BuildAMel on the vertical axis, the effect sizes, and the wetlands PCMel, the pre-constructed MEL, on the horizontal axis. And this dotted line shows that everything to this side of the dotted line, to the left and up, is an advantage for the BuildAMel. And everything to the right and lower is an advantage for the, or advantage, and I say that in quotations, for the pre-constructed MEL. And everything along the line is about the same. What we'll see is that we have really a much stronger link in terms of effect size, in terms of plausibility post to knowledge, which we also like to see, and less reliance, as I said before, on kind of their pre-plausibility ratings. They're not relying as much on their prior knowledge and their prior plausibility judgments, which may indicate plausibility reappraisal. Again, this is pilot test results. We're not completely satisfied. We're only seeing about a 5% gain in knowledge. When we did the pre-constructed MEL in the earlier project, we saw upwards of 10% gain, which is fairly sizable considering that these activities only take about 90 minutes of instruction time. In addition to the quantitative analysis, the project team is also conducting analysis that's mixed methods using the audio and video recording. This is a very time-consuming process, of course, because we have to transcribe all of the audio and video data. We have 3 video recorders that are involved, one the whole classroom, one the teacher recorder like you saw, and then also there's audio recorders at each student table. And what we do is, one of the studies that we've looked at, led by Donna Governor on our research team, is taking looks at specific dialogue terms to try to get some kind of inference about argumentation. And we do this by using systemic functional linguistics. And this helps us gauge the students' negotiations in the context of scientific argumentation. It's a very rigorous, robust process, very time-consuming, but really results in a rich data set that we can make some strong inferences from. And these move qualities are part of the codings of the systemic functional linguistics to help us get some inferences about that. We also do quantitative analyses based on our qualitative analyses and what we're seeing with those terms. And what we do is we link the discourse codes as relational ties via what we call adjacency matrices. And we do this in a social and network analysis methodology that's quantitative. So for example, we can see differences between students doing the fracking pre-constructed MEL and then later doing the fossils BuildAMel, where one student dominated the group. That's the size of this circle. And there was just really an interaction between students 1 and 2, and then some between the teacher. What we saw in the BuildAMel was less centrality of student 1, so less focus on that student, a more equal distribution amongst the collaboration, and less reliance on the teacher. We're currently working on writing this up, and this effort is led by Ananya Mateos. In addition, the team also works very hard to take the research that we do and make it useful for classroom context. We develop a lot of materials for teachers. Some of those are video materials available on our website, project website, but we also work in collaboration. For example, this is the Earth Scientist. It's a peer-reviewed publication for Earth and environmental science teachers, and we make these special issues that we do with them freely available to teachers for download, and you can download them too. We did one in 2016, in the fall of 2016, and then there will be a new one coming out in fall of 2020 that will talk about the BuildAMel activities. So COVID has really hit all of us very hard. It's hit our research team hard as well, particularly at the end of the school year when classes were canceled. We got about 75% of the data that we anticipated collecting in year 3, and we're uncertain about what's going to happen in year 4. But we've collected a lot of data, and we're continuing very hard to analyze these data. And we would just encourage you to learn more. This has been a very quick highlight of what we do. Please come to our website, the Science Learning Research Group, at sciencelearning.net, and you can find out the latest and download some more details about what we're doing. And I'd just like to close by saying that educational researchers and educational practitioners are needed now more than ever. We need to really help learners be more critically evaluative, to reappraise their epistemic judgments, either about source or about knowledge claims, which my team works on. And we need to work on constructing scientifically accurate knowledge. The stakes are just too high. This image that I'm showing you here is freshwater availability around the globe. And you can see it's not proportional, particularly in Africa, where freshwater availability is rare. But even if you were to focus on the United States, you would see that it's not equitable within the United States, freshwater availability. You've all heard about the Flint, Michigan crisis. There's been crises in freshwater in Philadelphia, Los Angeles, major urban centers, and they disproportionately affect the Black population. They disproportionately affect Hispanic populations, and this is not fair, and it's not right. So we need to think about how we're going to solve these problems in a manner that's critical, equitable, democratic, and promotes diversity. These are pragmatic solutions, and by pragmatic, I mean solutions that benefit society and benefit not just the local community, but benefit the regional communities and the global communities as well. So I really appreciate you listening to me talk today. I appreciate your patience as I worked as I presented via video, and I look forward to the live question and answer session that will be occurring later on. Thank you,